Hello friends, in the last class we derived the Gibbs-Duhem equation from the basic definition of partial molar properties and Gibbs function, and we derived it both in terms of the Gibbs function, where the equation looked something like summation of ni d mu I equal to 0. You can just go back to that slide and take a look at that. Yes. So from the Gibbs function, which is defined, partial molar Gibbs function, which is defined as mu I is equal to del G by del Ni, and the Gibbs function of the mixture that is defined as summation of Ni Gi bar, we wrote this expression, which is differentiating this Ni d mu I plus mu I d Ni. But from the basic fundamental law of thermodynamics, we wrote the G is v dp minus s dt plus summation of mu I d Ni, and comparing these two, we were able to eliminate this mu I d Ni and say that this part is equal to this part, so v dp minus s dt minus summation of ni d mu I is equal to 0, or when t and p are kept constant, these two terms would drop off, then you get summation of ni d mu I equal to 0. Right? So this at constant Tp. Okay, so this is called the Gibbs-Duhem equation, and we tried to derive this in a slightly more generic form in the same way, taking any general extensive property x. So when x was g, what we derived in the previous slide was correct, and when for any x, which is could be v, could be u, could be h, for any of these, if I do this, then I get the same kind of expression, summation of xi ni dxi is equal to del x by del t dt at Pn and del x by del p dp at Tn. And now when temperature and pressure are kept constant, these two go off, and this is the expression that you get, summation of ni dxi. So you get ni dv I bar is 0, ni dg I bar is 0, ni du I bar is 0, ni dh I bar is 0. This is a more general expression. So you get ni dxi bar is 0. Now this actually tells a very fundamental thing, which basically is that the changes in any of the partial molar properties cannot be done independent of the other, and all of them are interrelated using this equation. This is the Gibbs-Duhem equation. It's a very, very fundamental equation that we had derived. So it is as important as the fundamental law of thermodynamics, which we wrote in this form, So the Gibbs-Duhem equation defines, in addition to the basic fundamental law of thermodynamics, the way in which the changes in the various partial molar properties are related to each other. So you cannot change the partial molar property of one substance, keeping the partial molar properties of all the other substances the same, or in other words, you cannot change the chemical potential of one species in the mixture, keeping the chemical potentials of all other species constant. So it always, the change in one ends up affecting the other, and for that reason, if I know the chemical potential of one substance in a mixture, then using the Gibbs-Duhem equations we should be able to derive. So this, you can see, is a set of equations, not just one. So using the Gibbs-Duhem equations, you should be able to calculate the changes in all the other properties. So that is something that we saw in the last class. And then when we looked at the measurement of the partial molar properties, we took the example of a binary mixture and showed how systematic measurements of partial molar properties can be made, starting from the measurements of the specific volume or the partial molar volume and partial molar internal energy. So they can be measured by keeping all the other parameters constant and changing only the number of moles of one species, and measuring the change in volume and measuring the change in internal energy due to that, and using that we can derive the partial molar properties. So this then helps us to determine the partial molar Gibbs function as well. So we can then write, if I from this equation, that dg is equal to v dp minus s dt plus summation over I is equal to 1 to n of mu I dni. Okay, so this is something that we wrote in the last class. So in this we were able to write this as del g by del p at constant t and n, where n is I is equal to 1 to n, all species numbers. And similarly we could write this minus s as del g by del t at constant p n, and this mu I of course was del g by lni when t p and n j not equal to I are kept constant. Now using this, if I write the cross derivatives like we did for deriving the Maxwell relations, del square g by del p del ni would be identically equal to del square g by del ni del p. Now in this is del by del p of del g by del ni. Del g by del ni is mu I, so I can write this basically as del mu by del p or del mu I by del p, okay, when temperature and species numbers are kept constant, is equal to, this is del by del ni of del g by del p, right, and del g by del p is nothing but v here, so it becomes del v by del ni at constant t p and j not equal to I. And this we recognize as the definition of the partial molar volume of species I. So we can actually write del mu I by del p is equal to, at constant t and n, is equal to the partial molar volume Vi. So if I can measure the partial molar volume Vi, it gives me a method to determine the mu I by writing this as d mu I at constant temperature is equal to Vi dpi, Vi dp, right? So this is your expression that you get. Okay, so this is a method which tells you that there can be an evaluation of mu I using this expression. So if I integrate this expression from a certain reference state to the current state, so I'll get mu I minus mu I reference. Okay, so that is the reference side will be an integral from p ref to p of Vi bar dp. Okay, so if I can measure the partial molar volume along an isotherm, this is at the same temperature, right? So along an isotherm that is keeping the temperature constant, if I change the pressure from p ref to p and at all locations measure the Vi bar and then do an integration of Vi dp, then I get the change in chemical potential from the reference state in this. And if I say mu I ref is 0 at some particular state, then I can calculate the value of mu I using the volume measurement of partial molar volume. So we said how to measure partial molar volume in the last class. So using that, you would be able to get the chemical potential. And once I know the chemical potential, then from the chemical potential, using the property relationships that I have already derived, I should be able to write all the other expressions. So how do I do that? I know that Gi bar, which is the partial molar Gibbs function, is identically equal to mu I by definition. And we have also said Vi bar is equal to del mu I by del P at constant T and N. So this is, once I have mu I at at different locations, and we know how mu I varies with P, and I should be able to evaluate Vi. Okay, so that is the thing. Or in other words, we can get mu I from Vi using this expression. Then once that is known, I should be able to get Si bar is equal to, again from the same expression that we have here. In this expression, we said that minus Si is equal to del G by del T, right? So which is, and therefore the same kind of cross derivative expression will basically give me, that is, if I write del squared G by del T del Ni is equal to del squared G by del Ni del T, and I know this is del by del T of del G, this is del mu by del T, and this is del by del Ni of del G by del T, which is minus S. So this is minus Si bar, right? So this is the expression that I have. This is del by del Ni of minus S. Okay, so the negative sign take note. This is del S by del Ni at constant temperature, pressure, and Ni, and therefore that becomes the partial molar entropy. So the partial molar entropy is equal to del by del T of mu I. So that is the expression that I am trying to write here. So this will be del mu I by del T when pressure and N are kept constant. So these three come from the same equation, and from there we can write the other expressions from the derivative definitions. So H or Hi bar we can write as, so we know G is H minus Ts, so it will be Gi bar plus Ts plus T into Si bar, right? So you can, and this Gi bar we know is already mu I from here, and plus T into this Si bar, okay, it has the negative sign here, minus, so this plus will become a minus here, minus T times Si is del mu I by del T at constant P and N. Okay, so this is a method to get Hi. Once Hi is known, I can find out Ui. Hi is equal to Ui plus P into Vi, and since I know the expression for Hi, I'll be able to write Ui is equal to Hi minus PBI. So let me just modify this expression here. So this is okay. So this is Ui, which is partial molar internal energy, is equal to Hi minus PBI, sorry. And this will be equal to, this is Hi, and this is Vi, and therefore we can write mu I minus T into d mu I by dt minus P into d mu I by dP. So that's an interesting expression, mu I minus T del mu I by del T minus Pi del mu I by del T. Okay, and the last one which is remaining is AI, which is ui minus psi, okay, all partial molar. So that can be written from this ui, which is this expression, minus psi. Minus psi will become plus t into this, so this term will get cancelled. So it will become simply ui minus p into del ui by del p. So once I get the value of mu I from one of these expressions, all the other quantities can be evaluated from that. So from the knowledge of chemical potential, all the other properties can therefore be evaluated. So that is the thing about chemical potential and usefulness of the chemical potential in deriving the various quantities. But if I go back to the expression that I just wrote for chemical potential, this is an integral of Vi dP. So this is the expression that we have. So as pressure tends to 0, in this case Pref, where it can normally be integrated from the ideal gas limit, this B goes very, very large, okay, and therefore the mu I may tend to infinity. And on the other hand, when the mole fractions of the individual species become small, then this Vi can get extremely tiny. So the range of values of mu I is quite large and extensive, and therefore it becomes quite difficult to handle as a variable. So quite frequently we substitute for this mu I by a variable whose bounds are not as large as the chemical potential. So you define a new term for doing that by defining a variable called fugacity. Okay, so the fugacity is nothing but a variable that is defined in order to be able to handle the range of values that mu I can take within finite limits. So in order to understand fugacity, we'll now for a moment stop talking about mixtures or multi-component systems, but first talk about pure substances, starting from this expression. Okay, we'll go from this expression and so write it for a pure substance. So for a pure substance, what will happen? This Bi bar will be basically the molar specific volume. Okay, this is the volume per unit mole of the pure substance, which would be equal to this mu I can still remain as mu I. So basically mu I is Gi bar, and for a pure substance this will be molar specific Gibbs function, which is Gibbs function per mole of the substance. So we can just keep this as mu I itself. So this will be del mu I by del P at constant T. So this will be your definition, del mu by and the I is not required when we are actually writing about a pure substance, so this I can be removed. So it will basically be del mu by del P at constant T. Okay, so we'll start from this and discuss about pure substance first. We'll define fugacity for a pure substance and then come back to understand fugacity for multi-component system. Okay, so for a pure substance, then we can write dG, the molar specific Gibbs function, the change in that is equal to V dP minus S dt from the same expression that we had written earlier. So and since dG is the same as d mu, we can write it as d mu is equal to this, and therefore d mu T, which we basically wrote in this expression, this d mu T would actually be V dP at constant T. So that's the thing that we will write, and this will be equal to V dP. Okay, the same expression that we have here, d mu t, is basically when this delta t becomes 0, so it becomes v dp. Okay. Now let's start from an ideal gas. What happens in an ideal gas? In an ideal gas, P V bar is equal to R T, right? So V bar can be written as R T by P. So I'll take this P down here. So it's R T by P. So I'll substitute for V here. So this becomes d mu T is equal to R T dP by P, and this you can write it as R T d of log P. Okay, so this is the expression for an ideal gas. So if we want to write the same expression for a real gas, then this is not RT by P, it would vary from that. So for a real gas, if I want to keep the retain the same form, then I'll introduce a new variable in place of P as fugacity. So for real gases, let me write d mu T is equal to RT d of log F, where F is called the fugacity. So what do we understand? In the limit of ideal gas, that is as the pressures go smaller and this goes to real gas, the fugacity becomes the pressure, and so the fugacity also has the same units of pressure. So if we subtract these two, or rather we integrate these two expressions, you get mu is equal to RT, so at constant temperature, so along an isotherm, integrating along an isotherm, so this will become RT into log P plus some constant, which is a function of temperature, and here again we get, so this is for the ideal gas, let's call it as mu star. Okay, and for the real gas, let's call it as mu, which is equal to RT into log of F plus the same constant C of T. So if I subtract, I'll get a mu minus mu star, where mu is at in the real gas state and mu star is in the ideal gas limit. You will get an RT log of F by P, and this constant will get cancelled out. So this you get, and if I call this F by P as a fugacity coefficient, okay, then this can be called phi, then this is RT into log of phi. Okay, so that is your expression for mu minus mu star, where mu is the chemical potential of a real gas at temperature T and pressure P, and mu star is the ideal gas limit value of this. So in the an ideal gas pressure P, let us say this is this. So this is the expression or the definition that we get, where phi is called the fugacity coefficient. So in the ideal gas limit, this log of F by P should go to 0, or P should be F push F should become P. So we can write it here in the ideal gas limit. F tends to P, and therefore log of F by P becomes equal to log of 1, which is 0, and therefore we can say, okay, this is not instead of equal to, write it as tends to. Okay, so basically this is the expression that we have, that the d mu t is RT d log f as the definition of fugacity, with the limit that, as in the ideal gas limit, log of f by p tends to 0, together form the unique definition of the variable called fugacity. Okay, so this is the expression that we have. Okay. Now, in order to evaluate fugacity, we will basically use the same expression that we have got here. So d mu t is basically v dp, but then that is also equal to RT d log f. So this is the expression that we will basically write. So evaluation of fugacity of a pure gas Okay, so this is a pure gas rather. So you will get d mu t, that is a change in Gibbs function, change in partial molar Gibbs function, in this particular case molar specific Gibbs function at constant temperature, is written as v dp at constant temperature. This is along an isotherm, and this is also equal to RT into d log f, okay, at again constant temperature, right? So using this, and if we try to integrate this expression from very low pressure where the gas would behave like an ideal gas, let's call that pressure as P star, and the current state. So this integration, so we'll just leave the d mu t out as of now and look at only these two parts. So then I'll get an, along an isotherm, I'm going to integrate this RT into d log f is integrated from f star to f, so you get a log f by f star, okay, where f is the fugacity of the gas at temperature T and pressure P, and f star is the fugacity of the gas at the same temperature T but at a very low pressure P star, where the behavior is close to ideal gas, and this is going to be equal to integral of v dp, okay, integral of v dp at along an isotherm from pressure P star to the actual pressure P, right? So this is your integration that you will need to do. And if I write this expression saying that integral of v dp by integration by parts, integral of v dp is equal to pv minus integral of p dv. Okay, so this is basically the expression that we'll write by doing an integration by parts formula. Then this PV, in the you're applying the limits, ideal gas limit to the current one, you will get PV at the current state minus P star V star at the ideal gas limit. Okay, so this is the first term minus integral again from ideal gas limit V star to V of PD. Is that right? So now if I if I know the equation of state in some form, let us say a van der Waals equation of state or Lee Kessler equation of state or any kind of equation of state, if I know the pressure as a function of specific volume, then I should be able to integrate this expression and substitute these to get the correct value of the RT log f star by f, which is basically difference between mu minus mu star, which is mu is the chemical potential at the current state and mu star is the chemical potential at the ideal gas limit. So this is the expression. So I can evaluate this by for example 1, if the functional form of P as a function of V is given, this can be integrated. And in the ideal gas limit, this f star would actually become P, and therefore the expression that you get would be RT log f by P, and since P is known, so it will become actually P star. So P is known, so you can actually get the value of f. So that is the first method. The second method is using the compressibility chart. So you say that d mu T is equal to V bar dP at constant T, which is equal to RT d of log P at constant T. Okay, and now if I rewrite this expression by taking this dP here, okay, so you get RT d log f over here. Okay, if I take this thing here, then I'll get an RT d log f by dP. Okay, so then I can take the RT to the other side. So this expression will basically give me d of log f divided by dP is equal to V bar by RT. Okay, and if I use the compressibility chart saying PV is equal to ZRT, then I can say RT by P is RT by V, V by RT is Z by P. Okay, so this V by RT is nothing but Z by P. Now if I subtract 1 by P from both sides and then start integrating this, so then I'll get okay, I multiply throughout by dP, so I get a d of log f minus dP by P. If I subtract dP by P from both sides, I'll get Z dP by P minus dP by P is what I get on both sides. So then I'll be able to write this as d of log f, and this is d log P, so d log f by P is what I would get, and this would become equal to, on the other side it will be Z minus 1 into dP by P. Okay, and the dP by P can be written as dPr by PR, and since Z minus 1 is a function of PR, I'll be able to get this log of f by P by integrating this over PR from the limit of 0 pressure. So d log f by P is equal to Z minus 1 into dPr by PR, and if I integrate this from limits of 0 pressure to the current pressure of log of f by P, okay, this is d log f by P, which gets log of f by P, is equal to integral from 0 to PR of Z minus 1 into dPr by PR, and this we are capable of integrating because this Z minus 1 dPr by PR, this Z is a function of PR at any given TR, and we are going to integrate it along an isotherm, and therefore we will get this. So what we get here is log of F by P, okay, is equal to this integral. Okay, so and since this integral can be performed, we actually have, this is nothing but log of phi, which is the Fugacity coefficient. So actually you have what is called the generalized Fugacity chart. So if I know the value of PR and TR, I should be able to calculate, read out the value of phi from the generalized Fugacity chart, and from there I can evaluate the value of F. Okay, so this is a second method of calculating the Fugacity. The first method I told you is knowing the functional form. So if I have, for example, the van der Waals equation of state, or the equation of state in the forms that we wrote, Redlich-Kwong or Redlich-Kwong-Suave, or various forms of equation of state, then we should be able to integrate that. The second form is to write it in terms of Z, and using the generalized compressibility chart expressions to evaluate this expression. The third method is to write the definition of, so let me call it as method 3. You write G is H minus Ts, and therefore we can actually write mu minus mu star is actually G minus G star is equal to RT into log of F by P, okay, after the integration. Now this mu is nothing but G minus H minus Ts and this mu star is nothing but H star minus Ts star at the same temperature. So we can regroup this as H minus H star minus T into S minus S star, and these can be written in terms of your correction charts as minus of RTC into H star minus H by RTC. Okay, so these are actually molar quantities. Okay, so this is H minus RTC. So this term is like this, minus this T is as it is, and again you write an R, and this becomes plus into S star minus S by R, right? So this is what you get. So so you get an RTC times this, and this RT times this is equal to RT log F by P. So if I cancel out the RT throughout, I'll actually get a Tc by T, so it will become a minus 1 by Tr multiplied by the enthalpy correction, H star minus H by RTC, plus this RT gets cancelled, you get an S star minus S by R is equal to log of F by P. So this log of F by P can also be evaluated by knowing the TR and PR from the enthalpy and the entropy correction charts. So given the value of temperature and pressure, I'll be able to get the fugacity from this. So we have now defined fugacity for a pure substance and understood how to obtain the fugacity of a pure substance from the charts of generalized correction, either the generalized fugacity chart or the generalized enthalpy and entropy correction charts. So at the moment we'll take a pause here. We will in the next class come back with how to determine the fugacity of a substance that exists in a mixture, and how to evaluate the fugacity of a substance as it exists in the mixture in reference to its pure state and reference state. So we'll look at that in the next class. We'll stop here for now.